I begin, I want to lead with a question. Is there anyone in the room here that enjoys being on a long flight? Nobody? Me neither. Today, if you want to travel from New York to London, that's 8 hours. That's long. And if you're like me and you want to get home to India, that's just the beginning of your problems. But imagine if you have a hypersonic flight that can travel at the speed of 5 times the speed of sound at a minimum, which for the way Texans drive, that's at least 50 times the speed your car goes on the highway. That sounds awesome, right? But before we get there, there's some key challenges that we need to solve. And to do that, we need measurements on what happens on the flow that is traveling along these vehicles at these speeds. To get that measurement, it's super challenging because this environment is complex. The gases are atomizing, there's high temperatures, high pressures, and we need really good data, and collecting them is expensive. Now, to help solve this problem, I'm super motivated because it's not just a research problem. For me, it's personal. That brings me to global surface measurements on a hypersonic vehicle. What we're doing here is taking a model geometry that is the IC-3X, or the initial concept vehicle released by the Air Force, and we've scaled it down to fit nicely in our wind tunnel test section that was already described by Angie, so that's sitting right there. And using some techniques, we are trying to estimate these quantities like pressure and temperature at an angle of attack of 5 degrees. Now, traditionally, the way we conduct these measurements is we instrument them with probes. Imagine just hundreds of wires and bulky instrumentation, making it really hard to keep track of. But we've skipped that part. And what we're doing here is using these two cool techniques called pressure-sensitive paint and temperature-sensitive paint. We're literally just painting the model, illuminating it, and we're studying pressure and temperature profiles. I'm not going to give you all the details of how that works because Nathan's going to do that next. But just to get to the results here, we're looking at a pressure profile on the IC-3X. Now, because of the way air molecules along that IC-3X geometry is sort of compressing and expanding and traveling at these speeds, we get different zones. So we have the high pressure zone right at that nose tip there. And then moving along as the flow expands, we are seeing some reduction in pressure. And then on the fins, again, when it's offering blockage to the oncoming flow, we see some high pressure zones. So that's the pressure sensitive paint results. Instead of having so many sensors, we are just putting paint on there, analyzing the data. Now I can just pick the points as these virtual sensors and plot pressure histories over time. And the same thing for temperature. I can estimate the surface temperatures when they are experiencing Mach 7.2. So in conclusion, we found out where the highest pressures and temperatures are. Now we can give it to machine learning model developers who can then use this data to do cool things and get me home soon. Thanks so much for being here.